I didn't get the chance to introduce myself on Monday. I'm a physical oceanographer, and today I'm here to talk about OceanHeat content. Specifically, I'm here to talk about this international collaboration to try and advance mapping methods to create estimates of OceanHeat content change. You have heard a lot in the morning from Michael about spatiotemporal mapping, and now here we will see why this is such an important topic. We will see some of the results from the mapping work with Michael and Tia, and we will see some of the results from this assessment that we are doing of different mapping methods. So this MapEval4OceanHeat, and sometimes in the presentation it's going to be indicated, and I'm going to say as ME for OceanHeat or ME for OH is written on the slides. This is an international collaboration that started as an IAPSO study group to identify best practices in mapping oceanic fields. So some of the results in this lecture are actually from this work. So I want to, it's a large group of people, I want to acknowledge at least the other co-chairs that with me are leading this effort, Didier Monselsan, Matt Palmer, and Katia Dominguez. And also I want to acknowledge who created real products in some of these slides. And you can notice that our product that Michael described in the morning, is used also as part of this. So you'll see Michael and Tia Sukianto are in the list. So we'll briefly discuss why all of this we care. We will describe what method we have designed to go about this evaluation of different mapping methods and some results from that. We'll also describe and discuss altogether how this framework that I'm going to introduce is helpful to evaluate uncertainties about different mapping methods. So, as Michael pointed out, and specifically discussed for Argo data, so the Argo data come from these profiling flows that have revolutionized the way we observe the global ocean. Observation in the ocean is sparse, and this is the case especially before Argo. Michael showed how even during Argo we still are dealing with sparse observations, and the details of how we go about producing maps from that are important. But this becomes even more important when we want to go back in time. So here are the profiles available for temperature and so for OceanHeat content in different, different times, and we can see that we have very sparse observations before Argo, and then in 2010 we have Argo, and we get many more observations. We get less seasonal bias in how these observations are distributed, and the colors here of these dots go by the month of the year. And this is for ocean temperature profiles in the top 700 meters. As you go deeper, the situation is worse. There are fewer and fewer observations. Argo, if you are familiar with that, the core Argo program covers up the top 2,000 decibel, top 2,000 meters of the ocean. There are other products, programs within Argo, like the Deep Argo mission tries to go below that, but we have way fewer profiles that actually observe, that are part of the Argo and observe below 2,000 decibel. So why is this important? Why do we do this? If you are interested, I put here the reference of this recent paper by Maria Hubertol, where as part again of an international collaboration, we looked at different ways to estimate OceanHeat content. So I'm now going to go through the details, but you see a long list of products, and one of that here is the product that we developed with Michael and Tia. So everything that Michael has talked about goes in this local GP from Gaussian process regression. And what we see here that even if we focus over the Argo period, so the first time step here is 2005, this is a yearly time series, and this is OceanHeat content, we see that there is quite a spread in how the OceanHeat content evolves in time, in this OceanHeat content change. And we really care to get this right because all of you know that the climate is warming, so there is excess energy in the climate system, and more than 90% of this excess energy in the climate system is stored in the ocean. So keeping track of how the OceanHeat content changes is very helpful to understand the Earth energy imbalance. You may have heard of this term that basically wants to describe the fact that more energy is coming in the climate system than going out, so there is an imbalance at the top of the atmosphere. Most of that excess energy goes in the ocean, and that's why it's important to try and quantify in the best way we can, try to leverage the information we have in the best way we can to get an estimate of the OceanHeat content change that we trust, and not only the estimate itself, but also the uncertainty on that estimate. So monitoring the global ocean heat uptake is one of the big reasons why we care about this. We care about assessing the mapping methods that are being used for this problem. Also, if you think about climate projections, we have these emulators in the IPCC 6, and these emulators that produces climate projections are constrained, use some of the products that you see in that plot. So we want really that those products use best practices and that are as helpful as possible to constrain the climate emulators that are used to produce these projections. Also, if you think about decadal forecast initialization and system development in general for decadal forecast, for instance, the system at the Met Office, they use observation-based products to improve their system. So it is important to have products that, first of all, we think are a good representation of the real ocean, given the observations we have, and then have a good representation of the uncertainties that go with these products. And unfortunately, there is not only quite a spread in the estimate of specifically OceanHeat content, but not all the products do provide uncertainties. So this is something we, as a community, really want to improve on. Also for climate models and in general, ocean model development and evaluation, we want to have gridded fields that we can that we trust and that we can use to understand the model bias, for instance, and ideally that help us improve our models to better represent the real ocean. Finally, if you're looking for your own project and you're interested in doing some analysis of oceanic fields, you likely will want to use a gridded product for that instead of going back to the observations. Like mapping those observations are a big effort and maybe not the focus of your business. So you want to be able to use some product that is already available. And when you do that, I encourage you to think about strengths and weaknesses of the product you choose. And hopefully this framework that we have designed as part of MapEval4OceanHeat is going to be helpful also for you if in the future are interested in using an ocean content product, and hopefully in the future we will extend to our fields, and you can use that, for instance, if you want to map extremes in the ocean or other features of the ocean, you can get some information on the strengths and weaknesses of the product you use looking at this framework. So the fact that when you go about mapping observations, there are a lot of sources of uncertainty. The uncertainty could come from the data themselves. The uncertainty could come from the mapping method. in all of this, and also in Michael's presentation, the focus has been and is going to be on the uncertainty that comes from the way you map those observations. So you have sparse observations, you have to create continuous fields, and what are the challenges in there? What are the does it matter which method you use? And the fact that it matters is not a new thing. Already in this paper, they tried looking at different products, mapping the same set of observations with different statistical models. And they have seen that there is a spread. Here is shown that this spread is larger, especially in regions that are more difficult to describe from sparse observations to start with. So, the ACC, Western boundary currents, where the variability is high. That's where you would need, the most observations to do a good job to represent the variability. So, what are we? How do we move forward from here? So this project was looking at, okay, we have a bunch of observational products. If they all were to be produced from the same initial sets of observations, what do we get? What is the spread? And they find that there is a spread. But then now how do we move forward? How do we know which of the methods are closer to representing the real ocean versus not? And especially, how do we improve each of these methods so that if they are different from the real ocean, is not because some choice that they make that produces a bias in their estimate, a bias that can be addressed at least. So that's where MapEval4OceanHeat comes in. So our goals are to develop optimal mapping approaches for a wide range of applications. We saw some examples in the beginning of why all of these matters, and to evaluate strengths and limitations of oceanic content pumping methods and their uncertainty when they are provided. Because as I said, sometimes depending on the statistical model, it may be possible or not to provide principal uncertainties. So once, with this framework, obviously we can assess also, we get some information about our ability to constrain oceanic content change on a global scale, which is relevant for the Earth energy imbalance that we discussed in the beginning, but also at regional scales to understand regional changes in oceanic content. One of our main goals is to establish a community best practices approaches and improve the different data products that at least we analyze based on what we find to be a best practice. And to do all of this, we want to bring together scientists from different fields. So it's really nice to see, with this summer school here, we have a mix of different students from different backgrounds, including having, statisticians in the group. Because what you will find, hopefully, moving forward with your career, is that these collaborations, as challenging as they may be in the beginning, because you have different backgrounds, you speak different languages when it comes to science. Michael presented some of those examples of how we call objective mapping in one field, or in another field we call it cribbing. These are just some examples. You will find if you collaborate with others that are slightly away from your niche, that they may use a different language, but it's very well worth going past those barriers and collaborating, because that's how we advance science. So we bring in new approaches that maybe we haven't used in oceanography before. So this is, part of our goal, but what are we really doing? So we said in Savita et al., they already have shown that depending on the mapping methods, they get different results. So they go with the same input observations, they map them with different approaches, different results. But how do we move forward from there? How do we know which methods may do a better job to represent the truth? So the way we proceed in MapEval4OceanHeat is to use synthetic observations from a high-resolution model. And so we have our model here. And this is a high-resolution model, and I've not put a lot of emphasis on the details of this model, because eventually what we will discuss is that we don't we don't want to do this just with one model. We hope that we set up this framework, and it will grow to include more models that can be used to basically from this high resolution field create synthetic profiles. How do we subsample the model? We subsample the model based on the actual locations and timing of the real observations. So now we have this set of synthetic profiles, and we can go about and use, for instance, local GP, like the method we work on with Michael and Tia, to produce a map for that month. Then we compare the map or a metric computed by using this mapped product with the model truth, and we get some idea of how our statistical method does. What's the error in that statistical method when we compare to the model truth? So this is possible, obviously, only if we have a model truth to compare with, and that's why we went that way to finally introduce in these community intercomparisons one intercomparisons that includes the model truth and then allows for a better understanding of differences across the different statistical methods. I mean, oftentimes we hear about OHC when we want to understand the impact of observations in data simulated products. So they do, for instance, some denial experiments where they remove some data products and then they see how the data simulating system does, how the estimate changes if you remove some data products. Imagine like if in one of these data simulating systems, like, I don't know, ORS5 or ECHO, you remove Argo data. That's a large amount of observations. You will get a very different answer. So in here, this also can be used in the same way. These approaches can be used to say where would we want to put observations, right? Like where would it make the most impact? And this, in some sense, can be used in that way. Like we could do something similar where we tweak since we create this from the full model field, so we could tweak the distribution of observations and then see how our results change. So here we have a model that is high resolution. In this case, we call high resolution 1/10 of a degree. And it's daily. We cannot produce daily maps at 1/10. So what we do is to do some conservative remapping that preserves integrals over areas, so that in the end, what we actually compare is our nominal 1 degree resolution map with the conservative remapped version of the model at 1 degree and monthly. That's a very good question. And yeah, I was going to mention it later, but yeah, great that it came up here. We are going to do these comparisons. There is no way that we could achieve, daily resolution with this distribution of observations. So everything that I will discuss, and also, the application that Michael discussed in the morning, is monthly maps on a 1 by 1 degree grid. So yeah, that is true for both what Michael showed and what we will see here. So one thing is actually that I want to mention here, what Michael presented in the morning was only using Argo observations. We have developed our method only using Argo observations. When we use our method in this framework, we map this distribution. So we have more data than what we do like when we just map the Argo period. Okay, so we do this for 3 vertical layers in the water column, and this is approximate because the actual layer depends on the actual model layers. We have approximately about 300 meters, 300 to 700 and 700 to 2000. And we choose this because, as I said in the beginning, there are many intercomparison efforts that go on with real observations. And those are generally for instance, for the WMO state of the climate, we use these layers when we provide gridded fields. So we want to follow that choice. We use 3 different time periods. The longest is 1979 to 2014. Then there is the satellite period, 1993 to 2014, 2005 and 2014. The model ends in 2014. That's why here you see 2014. And we would want, as one of the other models and future models, to include more of the archival period. So then we mostly, all the products that have been included so far include temperature profile, use temperature profiles to map the ocean heat content change. One of the methods uses also SST and SSH. So as more information that goes into that map, and they use a random forest regression approach. So one of the predictors for the shallowest layers, they include as predictors also SST and SSH. Okay, so before we start to look at some of the intercomparisons, let's look at how the model does to reproduce some of the metrics from the real ocean. So this is, for instance, the model trend, and this is a trend over a short period of time. This is just over the Argo period within this framework, so 2005 to 2014. And we compare that to observations. In particular, we chose the observational products that also use SST and SSH because from the evaluation we have done so far, that is one of the products that can reproduce the model truth more closely. So we use it here also to validate. But we don't just compare the observational product with the model in itself, because these two will be different for two reasons. One, obviously, is that this is the real world. This is, a model, and it's not a data simulating model. So we, hope that it does a good enough job at represent reality, but it may also end up being different. These two will be different also because this one from observations, and this observational product was also chosen because it maps EN for observations, so a similar set to what we do with the synthetic profiles. This one is created from mapping sparse observations. So yes, we compare this to the model, but we also compare this to a version of the model that starts from the synthetic profiles from the model and uses the same method. So these two are more directly comparable just because even if this comes from model profiles, they both come from mapping sparse observations. In any case, if we look at the three panels, the top one and the two on the left, we see that in most regions, the model does a reasonable job at representing regional trends, which is great. When we look more closely to gridded product minus model, we saw that there are some differences and that there are fewer differences when you look at the version of the model mapped from synthetic profiles. So if these two were different, if these two maps of differences were the same, then it would just mean that observations and model are different because one is a map from sparse observations and one is the model with a full resolution in space and time. But instead we see that these two maps are not different, obviously, and that there are some differences in the actual distribution of these ocean heat content changes, of these trends. So yes, we have to be aware of differences. Nevertheless, the model does a reasonable job at representing many regions. Another thing I want to point out is if we look at the model standard deviation and the observed standard deviation, and this is the model standard deviation that comes from mapping sparse synthetic profiles from the model, what we notice right away is that so these two look somewhat similar. They look similar, but still when you map from sparse observations, you don't represent all the variability in the original field. That is something that we always have to deal with. Regardless of that, the actual observations show much more variance. So the model is not as energetic as the real world. So we have that to keep in mind. So let's pause for a moment and discuss in smaller groups some of the things we have introduced so far. So we showed that there is some bias in the model. So the question I would like you to discuss in pairs or groups of 3, depending on what is more convenient with you. Maybe, yeah, you can do pairs or 3, depending on where you're sitting. Are these experiments that we do as part of the MapEval4OceanHeat still helpful to evaluate the mapping methods and their uncertainties? If the model, so the model is the one that we use to create the synthetic profiles and eventually we map with different statistical methods, if the model has biases. In either way, why did you select that answer? And, depending on how much, we'll do this for a few minutes, so you may not get to this, but if you have time, you could also discuss what if regions of high variability in the model do not coincide with the regions of high variability in the real ocean. In an extreme case, you could think, what if the HCC is misplaced in the model compared to the real ocean? To think of an example. So we'll take a few minutes to chat, and me and Michael will walk around, so feel free to ask questions. I'll not go into the details, obviously, now, but there is also an ensemble mean here, that is the average of all the gridded products together. This is my ensemble of solutions, and then we do an ensemble mean and see how that fares. The black thick line is the model truth. So the nice thing about this approach is that we can compare with the model truth, so we can hopefully learn something about our statistical methods and their uncertainty and improve. So what we see is that for the Argo period in our simulation, that again, Argo period was way past this, but this is when the model is available. For the top 300 meters, different methods work reasonably well. Still, there are differences. There are regions where, for instance, only the blue line and this this brown line capture the trend in the true model, and the differences across methods become larger when you go back in time. Still, I want to mention that we can learn something from the Argo period. Like, if you think about what Michael discussed and the local GP product that we create with Michael and Tia, and this shown here, this line is displayed also for the bottom panels, because when you use the Gaussian process regression, you can learn those correlation scales in space and time during Argo when you have observations, and then you can use those for the other time periods. The time mean you always want to estimate for the actual period you're doing all of this, but as it turns out, if you use the decorrelation scales for the longer periods of time, you still, you don't perform worse than many other methods, and in many cases you perform better. So this hints that we can extract information from the better sampled period of time to then map the past. This is another example of regional trends. This is the model. These are the different products. So at the first glance, they all seem to, in some sense, to some extent, reproduce the model trend. If we look at the differences between each of these panels and the model truth, so for instance, for these products, if we do this minus that, we get that pattern. Here, when you look at these are maps of the differences in trend between each product and the model truth. What you see is that not all the maps look similar in terms of these anomalies being, these differences being showing a large scale pattern versus a more unstructured pattern. So going back to why we will do all of this, we would want that our methods, if they cannot predict in a certain region, is because we have very few observations. If we go into this estimate and we see structure in these differences, like large-scale regions where the colors indicate that the trend is larger or lower than the model truth, that is something that hopefully we can address, revisiting how we created that map. We kind of would want to see, patches, like the more speckle-like structures, the better, unstructured differences between our product and the model truth. because that is more representative of a situation where, yes, if I don't have data, that is what is going to happen. I cannot do a good job at representing the variability. So one thing I want to point out for this product, this is the one that also uses SSH and SST. They do a much better job at capturing the variability and trend in high variability regions. These have SST and SSH from satellite data. So on the other end, there are some patches of differences here, which we would want to get rid of. Let's look at the local GP that Mikkel described. We have problems here because the observations are sparse. We're only using oceanic profiles. So this is what it is, high variability region, sparse observations. You have challenges in reproducing the field that you're interested in. But then when you have more observations, if you look at the lower latitudes, then you tend to not see structural differences. This is good. It means that the statistical model is using the information optimally. So now I focused on these two. You heard about this, and this I wanted to focus on because it adds some information to the mapping. One take-home lesson could be that it seems, a very good idea to estimate the decorrelation scales from the observations. It seems also a very good idea to use SSH and SST information. Can we combine these two and create a new method that produces a better map and more in principal uncertainties? Because we know that for this one, we can produce principal uncertainties. This is produced with random forest regression, and this product does not come with uncertainties. So now, one idea could be extending the work that maybe Mikkel mentioned briefly, and Tia is actually introduced on Monday, where we can do this multivariate Gaussian process regression, where Tia is doing it for two different layers of the ocean. You use information from both layers to map the ocean, taking advantage of the correlations between the two layers. Why not do that with SSH and the oceanic content, and then hopefully get better maps? This is not super easy, because adding satellite data will add a large amount of data, and these computations are very expensive to do Gaussian process regression and estimate the decorrelation scale. Another example of what we can look at, trying to estimate, to understand better the uncertainty that comes from the mapping method, is to look at the root mean square error for different products. So each of these panels is for a different product, and we are looking at the root mean square error. One thing I will point out is that when you look again at this one includes the observation from satellite and SST. Very good idea. The colors are towards the blue, so lower root mean square error, and I don't show it here, but also high correlation. And then when you look at local GP, you do quite well, quite similar to that. Like here, you only have oceanic profiles. Here, you have much more information, but you still do quite well where there are observations. When you start going towards, highly energetic regions, higher latitudes, you have challenges. You have an increase in root mean square error. Finally, I want to point out one aspect that has come about quite a few times already in this discussion. When you look at the standard deviation of the actual model truth and you compare it with your reconstruction, what you see is that most of these maps are, and this projector maybe doesn't show it greatly in the back, but they have quite a bit of blue, meaning that in general, when you reconstruct a field from sparse observations, you will not be able to reconstruct all the variance in the observations. Do you see anything worrisome though? Is this map only blue, or are there some red patches in some of the maps? I see some nodding, there is some red. That worries us, because that means that the reconstruction has more variability than the model truth. So this is weird. Why would that be? Those are likely spurious month-to-month variations. So let's see an example. If we were to look at a 10 by 10 degree box somewhere and look at the black line in the back, and the back line is almost covered by the colored lines, because a lot of the methods have these spurious oscillations that come up. And the problem is that these don't only come up in a 10 by 10 degree box. If we look at this kind of plot for the global ocean heat content, the one that we are trying to connect with the Earth energy imbalance in terms of trend of ocean heat content and Earth energy imbalance, but also the top of the atmosphere variations with ocean heat content changes. Even in the global integral, you still see that the black line is almost covered by all the other lines, because many of these other lines have these spurious oscillations in time, even during the Argo period, that is the best sampled period. And you can quantify that looking at the leg one correlation and compare, the leg one correlation in the model is pretty high. Look at R1 in the other products. So local GP, what you heard from me, not too bad leg one correlation in comparison with the model. Most of the other products have a lower correlation. So there is that to keep in mind. Like, it's important to get this oscillation correct to model time. Michael showed some of that also earlier today. If you model in your covariance time, you can get some of this month-to-month variation closer to the truth. So since we're running a bit late in time, we'll do this more as a conversation with the full class instead of a think per share. But now we'll discuss how can, and then we mentioned some of these things, at least to some of you, in the conversations during the previous activities. How can an E4OceanHeat help improving ocean heat content and uncertainty? How do we connect all of this to the uncertainties? Like, all of this that we heard gives us some idea of the uncertainty that we get in our estimate from just not knowing what the optimal mapping method is. But how do we more in practice, come up with a quantity that helps us? So first of all, what Michael presented earlier today is that you can put uncertainty on this global time series of ocean heat content. This is for the top layer of Michael's presentation. So the uncertainties are this shaded area. As we mentioned in one of the other discussions earlier today, you can actually evaluate this in the framework that we discussed, because now you can say, okay, this is my model, statistical model reconstruction, these are the uncertainty. If I were to do this in the model world, does the model truth fall within that uncertainty? If it doesn't, you are not faring very well. Because your uncertainty is not very useful. You also wouldn't want that your estimated uncertainty from this ends up being much larger than the error that you have when you compare with the model truth. Because then, again, your uncertainty is too conservative. Tia gave some example of that when you, in her case, it was, to account for the correlation between two ocean heat content layers. If you quantify that correlation, you get a more accurate estimate of the uncertainty. If you don't, you have to go with the conservative one. You have to add the standard deviation of each layer to estimate the variance of the global ocean heat content, so the top and bottom layer added together. I want to point a reminder here, since we're looking at this time series, to stress out again what Michael pointed out in one of his slides. When you do this kind of estimates, your model choice matter. Not only in terms of what I just discussed a second ago, that you want to model time and the correlation in time in your covariance. If you don't, you end up with more of those spurious oscillations. You also want to choose your mean field well. So if you, for instance, here we have all Gaussian process regression, except the first one is a bit different how we do it. We try to reproduce another product. But all of these are within what Michael presented. The difference is that in one case, the covariance does not include time, so the space only do not include time, and the space-time include time. And since here there is a seasonal cycle, it's a little bit difficult compared to the previous slides to see that, if you don't include time, you have more spurious oscillation. But what is visible in this version of the figure is that these different lines, if you compare the ones that say no trend, so blue with green that has a trend, or red that has a trend that includes also quadratic trend, you see the trend in the output field, like in the global time series of ocean heat content, is quite different. So this trend is the one that we connect with the Earth's energy balance. So very important to get that right and to put uncertainty on that. So the choice you made in terms of using a trend in the time mean versus not really matter for this very important topic. So, this is something we want to, improve as a community. If we find that something is best practice, then it should be adopted, and the differences across methods shouldn't come from the fact that for some methods, a best practice is not used. The other important thing is that if you model time, you can put uncertainty. You model the correlations in time, right? So now you can put uncertainty not only, as Mikkel explained, on a global integral of something, but if you want to do a running average, a moving average of your quantity of interest, now you can do that, and you put the uncertainty correctly because now you have modeled the correlation in time. Otherwise, if you think about, just doing an objective map, first of all, if you do an objective map and you don't estimate the correlation scales in space from observations, you're not going to show anyone your variance map, because that will very much depend on the choice you made for the correlation scales. But also, say that you estimated those decorrelation scales in space. So now you can put, you have the variance of each of your point estimates. You cannot you cannot add a principled uncertainty in something like the 12-month moving average, because your model did not include an estimate of the correlation in time. So this is another example of what you can do and evaluate with this framework. You can have the map of your trend. You can mask the map based on the uncertainty, and then again, you can compare with the model truth and see if your uncertainty is reasonable when you compare it with the error from the map of the true field. And I'm going a little faster here in the interest of time, but we can come back. I'm happy to chat with all of you about any of this. So now, why do we care about all of this? Because it allows us to evaluate the mapping method and the uncertainty. I brought some example now here of how we can do that. The other thing is that I repeated many times in this conversation that we want to improve these mapping methods. And part of the reason why we want to do that is also that once we have an improved set of mapping methods where we kind of selected the best practices, and now at that point, the differences across methods are just because some things we really don't know how they should be done. So we adopt a method that is reasonable, but it may be different between one group or the other. Now we can create an ensemble of solutions for this, from these methods that have been improved, that they have been evaluated through a framework, they've been improved. Now we can create an ensemble, and then we can use the spread of that ensemble as a measure of how well we can constrain the quantity of interest. Because now at that point, we are confident that each method is following best practices. They are doing things slightly different. That's great. Now we can use that spread across method to evaluate how well we can constrain the quantity of interest. What would happen if instead we just take everything as is and use the spread across methods? And sometimes this happens, right? Like, what is the risk there? That maybe you are including a subgroup of these methods that have a biased estimate, and they are all biased because they are all doing something that is not necessarily best practice. Now, the uncertainty that you estimate from that spread across method is not going to be very helpful.